Hey everyone, in this video I am going to discuss the LeetCode contest, today's contest, that is weekly contest 504. So let's start with the first problem. The first problem is digit frequency score. Here you are given an integer n and you need to calculate the score of n, which is defined as sum of d into frequency of d, where d is the all of the distinct digits present in this integer n, right? And so your target is to calculate the score. So this is pretty simple. What you need to do is you just need to extract out all the digits from this integer n and then just calculate this sum over all of the distinct digits. So let's do it. So let's create an unordered map to store the frequency of the digits. D comma count is the frequency of this digit present in this integer. So the score, add this into the score, d into its count, and that and return the score. For first sample test case, the output is 5, true. For second sample test case, the output is 2, okay, true. Let's submit it. Great. So let's move to the next problem. Our next problem is the maximum number of items from sale. So in this question, you are given a 2D integer array items where items of I equals to factor of I comma price of I for the ith item, and you are also given an integer budget. There are unlimited copies of each item available for purchase. You may buy any number of copies for any of the items such that the total cost of the purchased copies is at most budget. After buying items, you may receive free copies according to the following rules. For each item I that you bought at least one copy of, you receive one free copy of every item j, such that j not equals to I and factor of I divides factor of j. And the second rule is buying multiple copies of the same item I does not give additional free copies through item I. Okay. The third rule is the same item j can be received from multiple times for free if it is received from purchases of different item types. At the end, you need to calculate the maximum total number of item copies you can obtain, including both purchased copies and free copies, while spending at most budget on purchased items. Great. So let's see the constraints. The total number of items are order of 10 to the power 3, and factor and price are also order of 10 to the power 3. They are less than equals to 1500. So some solution can work here, maybe n square or n into price or n into factor or n into budget. This kind of solution will work here. So let's understand the problem. We need to purchase some items, right? And the price of the items purchased must be in the budget. After purchasing, we may also receive the free copies, right? And for each purchased item, right, we can receive the free copies of any of the items whose factor is divisible by this purchased item, right? And we need to maximize this total number of copies we obtained. Okay, so first thing we need to do is for each factor, right? So let's say for each item we need to find the maximum number for each item purchased. We need to find the number of free copies we can obtain, right? So how can we find it? So let's say for an item we have factor and price, right? So how many free copies can we obtain for this ith item? The number of free copies we can obtain is the number of items whose factor is divisible by factor of I. So our first task in this problem is to find the number of factors in this items array which are divisible by this factor of I. So for this, let's create an array count, and let's also define a maximum integer 1500. Max, let's define it 1501. Okay, and let's make an array count array of 1501. So here count of array will store the number of factors, number of factor j, number of factor j in items array stores the number of multiples of, what should I say, stores the number of multiples of I present in items array, present in, let's say, factor array, factor of, or let's simplify this, let's say this is correct, but to make it more simple, let's say it stores the number, it stores the count of fact count of such factor j such that factor j is is divisible by I, right? You understand it, right? Count of I stores the count of such factor j such that factor of j is divisible by I, right? And what is factor of j? Factor of j is the factor of jth item. Now you know that any number is divisible by itself, right? So initially, let's iterate over the items array and assign the count. So let's say the factor of this element, increment the count by 1 because this number is divisible by itself, right? And now calculate which other integers are also divisible by this each of the integers. So iterate over I equals to 1 to max. Now we are going to calculate the count of integers which are divisible by I other than I. These are plus equals to I. So count of I plus equals to count of j. Why we are adding count of j to count of I? Because j is divisible by I, right? Now finally our count array stores the number of factor of j which are divisible by I. Okay, so this was the first task of our problem. Now let's come to the actual task we need to calculate, that is the maximum total number of items we can have, right, after purchasing some of the items. So for this, let's create a dippy array. This is dippy, and let's create dip of budget size, right? Dippy of I will store dpofy this state represents the maximum number of items we can have. dpofy represents the maximum number of items we can have of we can have from we can have uh, from I budget, right? Or let's say spending I, we can have from spending I amount of price, right? We have only spent I amount, and now from I amount we need to calculate the maximum number of items we can have. Okay, so let's calculate this. Let's iterate over the items array. And please notice one thing here, that we for now we only want to buy one item, right? And let's say if our after purchasing some of the items, right, if our budget is still remaining, then what will we do? From the remaining budget we will just buy the minimum price item, right? So let's also take an integer minimum price. Let's store it with initially take 1500 as the minimum price. So minimize it. Now calculate the DP array. Okay, so let's say we are purchasing the ith item, right? So if we are purchasing one copy of ith item, in this case our DP state transition will look like this. We have purchased the ith item, so how much money we have spent? We have spent this amount of money, u of 1. So our earlier DP state would have been I minus u of 1. And how many copies did we get? Total copies purchased plus purchased copies 1, and the other free copies, how many did we get? Total, how many did we get? Total did we get our count of u of 0. Why is it so? It is because count of u of 0 will store the number of factors which are divisible by u of 0, right? So, and this will be our number of free copies, right? If you see carefully, for each purchased copy we can get all of item j such that j not equals to I, and factor of j is divisible by factor of I. And notice that count of u of 0 will also store itself, right? Because we have added the number itself to the count array, right? So we do not need to add 1 as the purchased item one more time, right? So this is the DP transition. Also add a case here that for buying this item our budget should be greater than or equals to u of 1, right? Budget should be greater than or equals to price of this item. Okay, so once we have calculated this DP array, let's take an answer variable and iterate over this deep array. Here we should start with budget. So you know that dp of I represents the maximum number of items we can have after spending I amount of price, right? So let's maximize the our answer comma dp of I. Dp of I is the number of items we can purchase plus free copies after spending I amount of money. Now how many extra money we have left? We are left with budget minus I. This price is left. So from this price we will greedily purchase the minimum price item, right? So how many copies of the minimum price item we can get? This is the amount left divided by its minimum price. At the end, just return the answer. This is 2 into I. 4 and 10. Okay, let's submit it. Great. Okay, so I hope you understood this DP transition. So to make it more clear, this DP state, we are only purchasing only one copy of a item, right? Why are we not purchasing multiple copies of the same item? Because multiple copies won't buy you extra free copies. Only one purchase of each item can buy you extra free copies. So that's why in the DP array we want to purchase only one copy of each any of the item, and we want to maximize the total number of items we can obtain after spending I amount of money. And in this loop what we are doing is our dp of I, we know that dp of I is the maximum amount of uh, items we can get after spending I amount of money. Now from the remaining budget we will simply buy the minimum price item, right? The count of the minimum price item. So this is how we can simply get the total number of maximum items we can get from the total budget. So let's move to the next problem. This is a similar problem. The only difference here is that each purchased copy of item I can give you at most one free copy of another item J, right? Each purchased copy. So are you able to see the difference from the previous problem? The only difference is that in the previous problem, if you purchase one copy, then you can get any of the free copies whose factor is divisible by the factor of the purchased copy, right? And the previous problem you were given that if you purchase multiple copies of same item, then you won't get the free copies for the multiple purchased copies. You will only get once, right? But in this case the difference is each purchased copy of item I can give you at most one free copy of another item J. So let's say you purchased one copy of some item, then you will get some of the jth copy, right, as a free. If their factor is divisible by factor I, right? And the another difference is for each ordered pair I comma j, you can receive a copy of j from purchase of I at most once, right? So let's say you purchased I item 2 times, then you cannot get item j 2 times free of cost, right? You can only get each of the pair only means at most once, and the same item j can be received from j can be received multiple times for free if it is received from purchases of different item types. This is true for the previous problem also. Okay, so how do we solve this problem? For this problem, our total number of items are order of 10 to the power 5. So they are expecting us to solve the problem in linear or n log n time. So let's proceed how we can solve this problem. So first thing is the similar thing. We need to calculate the this thing. So this is the similar thing we will have to calculate in this problem also. That is how many other items factor is divisible by this current items factor, right? So this count we have already calculated. Now let's come to the main task of the problem we need to solve. That is the maximum total number of item copies we can obtain following these rules. Okay, so this time what we can do is, okay, so let's say mm, each item, for each item we can buy. So let's say if we purchase one of the so if we purchase one items multiple times, then we can get free copy of free copy of some more items, right? Multiple times. So how do we go about solving this? So first of all, we will start with purchasing the smallest price item, right? And suppose we bought the smallest price item, then we may be getting some free copies of other items also, right? Okay. Mm, so if we see this first test case, first sample test case, we have a budget of 19, right? So in this budget, what we can do is, uh, if we greedily purchase some of the items, so let's say here the factor is 1, but its price is 6. Its factor is 2, price is 4. Factor is 3, price is 5. Like, right? So what is the minimum price of an item? Minimum price of an item is 4, right? So let's sort these items in the increasing order of price. So then the array will be 2, 4, 3 5 and 1 6. So notice one thing. Let's say if we are going to buy any of the item, right? Let's say we want to buy this item. Then it is true that if we purchase one item of this kind, then how many free, if we purchase one item of this, then now let's before finding this, let's find how many factors are divisible by 3 in this array. There is only no factors are divisible by these 3. So we see that if we buy any of the item of this kind, then we will not get any free item, right? And if we buy this item, if you buy this item, then we can get this item and this item both, because 3 is divisible by 1, 2 is also divisible by 1. And if we buy this item, then also we will not get any of the free item, because 2 does not divide 3 and 1. Okay, so if we purchase this item, then only we will get free items. So our budget is 19, so let's purchase two items of this kind. So it will cost us 12 budget. And what if we, okay, 2, so it will cost 2, 6 to the 12, it will cost us 2 items. And how many free, if we purchase 2 items, then we will get 2 items free. This we can get and this we can get. So total 3 we get from this price. Again, second time, how many remaining budget we left? We are left with 19 minus 12, that is 7. For 7 we can purchase either of these. Either we can purchase this or this. We cannot purchase both because both will need 9. So any of the item we can purchase. So let's say we purchase this minimum price. So it will cost us 4, and it will give us only one copy, because after purchasing this item we can have only one copy, we cannot get any free copies. So for total of 16 price we get 4 copies. This should be the answer of this first sample. No, it is 5 actually. How are they getting 5? You can buy 2 copies of 0 and 1 copy of 1. 2 copies of, oh, we had bought 2 copies of this item, right? So how it is 3? It should be 4, right? Because 2 copy we bought for this and 2 copy we got as free. So this is 4. Then 4 plus 1, 5. Total we got 5. And this is our answer for this first sample test case. Okay, so if we think it carefully, what we can do is, here what greedy solution we can apply is, we will sort this items array in the increasing order of their price, right? And we will buy any of the, we will purchase any of the item if, let's say, there is a price, price of I, comma, let's say factor of I for the ith item, and this is the price. So, and this is item series increasing order, we have sorted it. Now we will purchase this item if and only if the minimum price element, 2 into minimum price element, this is greater than no, this must be minimum into 2. It was 2. So this, if this is greater than P of I, right? So then only we will buy one copy of this item. So why it is so? Why are we doing this greedy? It is true because let's say if we purchase one item of this kind, right? Then we will get, on one purchase we can get one free copy, right? One free copy. And for now suppose we can get multiple for now suppose that multiple other items are divisible by factor of I. Multiple other items factor is divisible by factor of I, right? So let's say it's count of, for now assume count of f of I, count of f of I is greater than 1, right? Assume this. Then we can say that if minimum price into 2 is greater than p of I, then we will buy one copy, right? And because otherwise, let's say if this is true, suppose if this would have been the case, if minimum into 2 is less than p of I, then we would have not bought, then we would not have purchased the ith item, because we can already get the minimum price element two times in this lesser amount, right? So this is the greedy approach we can apply for purchasing the items in this case. So let's solve this problem. Let's create a vector, and in this vector just store price and their count, right? So for each item, iterate over the items. In this price count vector, store the price, comma, the number of factors divisible by the factor of this item. Okay, because we need this here. Sort this vector. Okay, now let's take a variable answer for price, comma, count. Price, comma, count of factors which are divisible by this item's price. Okay, so first thing we need to check is that if price is, if price is this condition we need to check. If price is less than 2 into minimum, and also take a variable here, minimum price, and let's also assign it to 10 to the power 9. So minimum price we can always have this one here. Minimum price will be the first, minimum price is pc of 0 dot first. Okay, so if price is less than 2 into minimum price of an element, in this case only we will buy this item, right? So how many copies of this item we can buy? This will be our remaining budget divided by the price, right? Also another thing is, we would only like to buy the maximum number of its copies comma C minus 1. Okay, so do one thing here. Decrement count of I by minus 1. Why we are decrementing it? Because we want to remove its own factor, right? Because initially we had added count of I itself, because I is divisible by I itself. So remove 1 from here. Now count of I represents the count of such factor j where j is not equals to I, where j is not equals to I and factor of j is divisible by factor of I. Okay, so here the maximum number of copies we would like to buy is minimum of this thing, minimum of C comma the maximum number of copies we can buy from this budget, right? And why we are doing this? We are doing this because we will only buy because we want to get the free copies, right, out of this budget, right? And the maximum number of free copies we can get is this. Okay, so let's buy CP number of copies for this particular item whose price is P, and let's add these copies to our answer, right? So we have copies, we have bought CP copies, and for CP copies we will get CP copies for free also, right? And let's decrement the budget. The budget will be, the amount of budget will be decremented is CP into P. Okay, so this is the only thing. At the end, from the remaining budget, we will just buy the minimum price element and return it. Here the factor is order of the factor maximum value factor is items dot length. 5, and for second sample test case 7. Okay, great. So let's move to the fourth problem. Our fourth problem is lexicographically maximum MEX array. You are given an integer array nums. You want to construct an array result by repeatedly performing the following operation until nums becomes empty. Choose an integer k such that k is less than or equals to its length. Compute MEX of the first k elements. Append MEX to the result array. Remove the first k elements from nums. At the end, you need to return the lexicographically maximum array result that can be obtained after performing these operations. Okay, how do we solve this problem? So if you take an example of this first sample test case here, so to so we will use the greedy algorithm here. So greedily, so first of all, let's see the maximum, what is the maximum value of MEX we can get after choosing a prefix. The MEX value will be, the maximum MEX value will be the MEX of this complete array. What is the MEX of this complete array? MEX of this complete array is 2, right? Because 0 and 1 are present in this array and 2 is not present. Now find what is the minimum length of the prefix whose MEX is 2. that is 0 1, right? So our result, let's result array. What is the MEX of this 0 1? 2. Remove this prefix, then our nums will be left with only 0 element. Then we will, in the second operation, so first operation we applied for 0 1. Now the second operation we will apply on 0, and for 0 the MEX is 1. So this is our result array. Optimally we can get for the first test case, that is 2 1. Okay, so this similar greedy approach we can apply for a general array. So let's say we are given a general array nums, okay, and let's say its integers are a1, a2, a3 up to an, right? So first operation, so for the first operation, what you will do is you will calculate the MEX of this complete array, right? Let's say the MEX is capital M. Okay, now what you will do is you will using the greedy approach, what you will do is you will pick the smallest prefix of this nums array such that its MEX is equals to M, right? And you will just remove, let's say the index is IDX. So for the prefix of length IDX, you get MEX as M. So you will just remove this segment, you remove this prefix from this array. Now your after first operation, your nums will be like this: a of idx plus 1, a of idx plus 2 up to an. And in our result array, we will just append m. Okay. Now for the second operation, we will follow the similar approach. We will find the MEX of this. Let's call this M1. For the second operation, we will calculate the MEX of this remaining array. Let's say this is M2. We will follow the similar approach. We would like to find the smallest prefix of this array whose MEX equals to M2. Then we will follow similar approach. We will just append M2 here and remove this prefix. So we will keep on doing this until nums become empty. Okay, so let's see how we can optimally implement this solution. The maximum value of any nums integer is 10 to the power 5. Let's define it. Okay, and to optimally implement this solution, to optimally find the minimum prefix whose MEX is equals to M, let's do one thing. Let's store the index of each element, right? Index of each element in the decreasing order. So I equals to 0. Let's define n equals to nums dot size iterate over the indices of nums in decreasing order, idx of nums of I. So here what we are doing is we are storing the index of each element in decreasing order, right? Once we have done this, let's find the MEX, right? MEX equals to, initially let's say it is 0, and let's take a answer vector, right? Now let's find the MEX. Let's take the MEX, maximum MEX equals to 10 to the power 5 plus 2. So if IDX of I is empty, we will just break, otherwise we will increment MEX by 1. Why? Because ith element is present in this array. If ith element is not present in this array, we will just break and we will say that we have calculated our final MEX for this original array. Okay, now what we are going to do is we will so in we took the start index, right? What does start represent is start represents that we have removed all the elements before start, and now our remaining array is from nums of start up to nums of n minus 1. Okay, so let's run a while loop. While start is less than n, then we know that there is an array suffix which is remaining from start to end. We also need to remove this. So our first task is, we know that the MEX of this segment is MEX, right? So we need to find optimally the minimum, we need to find the minimum length of the prefix of this segment such that its MEX is equals to MEX, right? So how to do this optimally? We can do, what we can do is, let's take the maximum index equals to 0, right? And let's, so one thing here is, if MEX is equals to 0, let's handle this case separately. If MEX equals to 0, in this case we will remove one by one elements of this array, because is MEX is already 0, then we just want to maximize the length of our result array, answer array. So if MEX is already 0, then we will push back 0 and we will remove one element. Okay, and continue. After handling this base case, now we have MEX greater than 0. So in this case we want to find the minimum length of the prefix whose MEX is equals to this. So let's see how we can do this. The way we can do this is I equals to 0 to I less than MEX I plus plus MX equals to minimum of MX equals to maximum of MX comma IDX of I dot pack, right? Once we get this, we know that we will have to remove the MX, we will have to remove the segment, we will have to remove the prefix of this segment up to index MX, right? And first of all, let's push this MEX value to the answer array and remove the prefix indexes up to index MX from this index array, because we are going to remove, in this case we are going to remove this prefix starting from index start up to MX. So remove these indices. For I equals to 0 to mex I plus plus while, let's start from mex minus 1 I greater than equals to 0 I minus minus. So while index of not index of I dot empty नहीं है ये, and index of I dot back, index of I dot back equals to index of I dot back is less than or equals to mx, right? Because we are going to remove this, because we are going to remove this segment, so let's remove all the indices which are less than or equals to mx. So in this case we will just remove this index. If idx of I dot empty means there are no elements left in this array whose value is I. In this case, let's also assign the mex equals to I, because I is not present in this array now. Oh, right. So this will suffice our requirements for this problem. Let's run it. For the first sample, it is 21000. How is it so? Okay, so we forgot to assign the start to mx plus 1 because we have removed this segment. Okay, for the first sample 2 1, second sample the answer is 3, for the second sample, for the third sample answer is 0 0. Let's submit it. Okay, great. So we have solved this problem greedily. So yeah, this was it for this video. I hope you like the problem solution. If you have any further doubts regarding the solutions of these problems, you may comment in the video. That's it for this video. Thank you. Have a nice day.